Hello, my name is James York and I will be doing a math tutorial on the ratio and root test. So here's what we need to start using the ratio test. We need this sigma a to the n to be a series with non-zero terms. So, once we've had that, we can apply the ratio test, which looks like this. Now, once we do that, there are three possible outcomes. The first outcome is that this is less than 1, in which case the series will converge. Absolutely. The second option is that when you apply the ratio test, you get the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n equals infinity or is greater than 1. In either one of these cases, the series will diverge. The third option is you apply the ratio test and you get that it equals 1. In this case, the test is inconclusive and you will have to refer to a different test. So, now that we've seen how the ratio test works on a broad level, why don't we try some examples? We'll start with the first one. Here we have the sum as n goes from 0 to infinity of 2 to the n over n factorial. Now this, when you write it out and apply the ratio test, you get the limit as n goes to infinity of the absolute value 2 to the n plus 1 over n plus 1 factorial times n factorial over 2 to the n within the absolute value. As you can see, this matches what we had before. I just took a to the n because it was already a rational function and flipped it and multiplied rather than dividing. Now, simplifying this, you can cross off the 2n with this 2n here and you end up with 2 to the first. You can cross off this n factorial with this factorial, leaving you with just n plus 1, and you get the limit as n goes to infinity of the absolute value 2 over n plus 1. Now you take the limit as n goes to infinity, which equals 0, and that is clearly less than 1. So, going back to our original rules, we have here our first case, where the limit as n goes to infinity of a to the n plus 1 over a to the n is less than 1. So, using that rule, we can say that this function is absolutely convergent. So, here's another example. So, we'll apply the ratio test and do the limit as n goes to infinity of the absolute value n plus 1 squared times 2 to the n plus 2 over 3 to the n plus 1 multiplied by n squared times 2 n plus 1 over 3 to the n. Now, from there, we can simplify this to the limit as n goes to infinity of 2 to the n, 2 times n plus 1 squared over 3n squared. And as you can see from there, the limit equals 2/3, which again is less than 1, and going back to our rules, is absolutely convergent. How about another example? Here is something a little different. Now this right here should give you a hint that it's probably going to be something with e, or the natural logarithm, just to get us started on the question there. And why don't we try the ratio test? N plus 1 to the n plus 1 over n plus 1 factorial times n factorial over n to the n. Now this will clearly cancel that, but after that it gets a little more complicated. Now you have the limit as n goes to infinity of n plus 1 to the n plus 1 over n plus 1 times 1 over n to the n. Now you can take this, and it will cancel with one of these. So now you have the limit as n goes to infinity of n plus 1 to the n over n to the n, which equals the limit as n goes to infinity of 1 plus 1 over n to the n. Now the limit of there equals e, which is greater than 1. So, going back to our rules, here's what we have. We have the limit as n goes to infinity of a to the n plus 1 over a to the n is greater than 1. So what we're going to get is that function diverges. Here, so here's our last example. We have as n goes to infinity the sum of negative 1 to the n times square root n over n plus 1. And so if we apply the ratio test here, we get the limit as n goes to infinity of the absolute value of square root n plus 1 over n plus 2 times n plus 1 over square root n. So if we simplify that a little, we get the limit as n goes to infinity of the absolute value square root n plus 1 over n times n plus 1 over n plus 2. And if you take that limit, we get square root 1 times 1, which equals 1. So, if we take our rules that we made earlier here, bring them back in, clearly we have this last case, and the ratio test is inconclusive. So, we'll have to use some other test to figure out if this is convergent or divergent, because the ratio test is not useful. So as we just did the ratio test, you may have noticed that it was most useful when dealing with n factorial, because as you took the sum of that and applied the ratio test, you got n plus 1 factorial over n factorial, and that canceled, so that was pretty nice. It was also very useful when dealing with a number to the nth power, because as you applied that in the ratio test, you got something that also simplified rather nicely into this here. So we've seen when the ratio test is most useful. Now the root test is most useful when we have an a sub n that equals something to the nth power over something else to the nth power, say in this case a to the n over n to the n. So we can apply the root test, which you'll notice looks very similar to the ratio test, but instead of doing the absolute value of a sub n plus 1 over a sub n, you do the absolute value of the nth root of your a sub n, which in this case is a to the n over n to the n in absolute values. So this equals the limit as n goes to infinity of a over n. Technically plus or minus a to the n, but it doesn't really matter. It goes to 0, and that will be negative or less than 1, which is absolutely convergent. So this leads me to the rules that will dictate when you can use the ratio or the root test and what they tell you, and they're very similar to the ratio test. There's one less stipulation here where the series only has to be a series. It doesn't have to be a non-zero series, so that is kind of nice. And again, we have the three potential outcomes. The first potential outcome is that the limit as n goes to infinity of the nth root a sub n in absolute values is less than 1, in which case it is absolutely convergent, which is what you saw in the example, quick example that I just showed you. And the second potential is the limit as n goes to infinity of the nth root absolute value a sub n is equal to infinity or greater than 1, in which case it is divergent. And then the third option equals 1, in which case it was again inconclusive. So, as you can see, it is very similar to the ratio test, but it is used at different times, namely when you have here something to the nth power over something else to the nth power, rather than n factorial or something to the or a constant to the nth power. So here is a quick example. We have the sum of as n goes to infinity of 1 over n minus 1 over n squared to the n. So, as you can see from everything being raised to the nth power, the root test is going to be very useful here. And I'll put the limit as n goes to infinity of the nth root of 1 over n minus 1 over n squared to the n. Now those n's will cancel each other, and with the limit as n goes to infinity of 1 over n minus 1 over n squared. And what you'll get from that is 0 minus 0 equals 0, which is less than 1, and again we get absolutely convergent. Now, as you can imagine, something that equals 1 is inconclusive and greater than 1 is divergent, the same way as the ratio test worked. So I hope this tutorial has been helpful in navigating the ratio and root tests.